Okay, continuing with this section, talk about weak and strong interactions. So strong interactions, there's only one, and that is a covalent bond. So covalent bonds are strong interactions. So the only way to form a new strong interaction is by a chemical reaction where a covalent bond is formed between two atoms. So an example would be if I had two amino acids. These are two glycines, and through a condensation or dehydration reaction, I get a dipeptide. And you can see that a new bond has been formed between this carbon and this nitrogen right here. That is a formation of a new strong interaction. So strong interactions are just covalent bonds. Now weak interactions, we have different forms of weak interactions. The first one is hydrogen bonding. And the way to know if something is hydrogen bonding or not hydrogen bonding, for hydrogen bonding, it requires a hydrogen to be involved. So in this case, you can see here, this is a nitrogen with a hydrogen right here. And you would have a partial negative charge here, a partial positive here, and the oxygen here, you would assume that this oxygen possibly has a partial negative charge on it also, and you get the formation of a hydrogen bond between these molecules. Here's some more examples of hydrogen bonding interactions happening. Let's take a look. For example, here you actually have a negatively charged oxygen, hydrogen bonding with a hydrogen that's single bonded to an oxygen, an OH group. Here a nitrogen. Nitrogen is an electronegative atom, so you can imagine that possibly this nitrogen has a partial negative charge on it. Again, you have an OH group, a hydrogen single bonded to an electronegative atom in all cases. So it's a case here that the hydrogen is always single bonded, has a polar covalent bond, because it's single bonded to an electronegative atom. So we'll end up having a partial positive charge on itself. So that is a hydrogen bond, and it's an electrostatic interaction, because all you have is, in all these cases, if I were to go and for all these hydrogens here, they all have a partial positive charge. And all these things here are going to either have a partial negative or they have a full negative charge on them. And that leads to the formation of a hydrogen bond, because it's just positive and negative charges getting near each other, being attracted to each other, and sort of grabbing onto each other a little bit. So hydrogen bonds are much weaker than covalent bonds. And we'll look at the numbers for that in a second. Again, here's another example of a hydrogen bond where this is showing you two water molecules. We've drawn this before, where you have the partial, and there's a mistake in this figure right here. This should be a partial negative charge, not a partial positive. The book made a mistake. So you can see that the partial negative charge on the oxygen, partial positive, negative and positive are attracted to each other. You're going to get the formation of the electrostatic interaction. And in this case, we've classified as a hydrogen bond because you have a hydrogen involved in the middle. So what's an ionic bond? Ionic bond is basically any electrostatic interaction where you have full charges, permanent full charges or partial charges, that does not involve a hydrogen. So let's start out with a simple example. Na plus and Cl minus. There is a electrostatic attraction between the negative and the positive charge, right? Now, this can easily also be Na plus and a water molecule. And the water molecule, I'm just going to put this in a little different color so you guys, has a partial negative charge on the oxygen and partial positives on the hydrogen, but this electrostatic interaction does not involve a hydrogen. So it's not a hydrogen bond, it'll be an ionic bond in this case. Whereas this thing right here, Cl minus, this is going to be a hydrogen bond because you have hydrogens involved. So this right here is a hydrogen bond, H bond, whereas this thing right here is an ionic bond. So that's the difference. Again, you always have some sort of permanent charge involved. Full charge or a partial charge involved in ionic bonding, but in this case, instead of it being it's not a hydrogen bond because you're not going to have any hydrogens involved in that electrostatic interaction. So it's still an electrostatic interaction. I think van der Waals interactions are a little bit more complex to explain, but they involve electrostatic interactions also, but these electrostatic interactions are not formed because there are permanent partial charges on the molecule. So in the case of water, you have permanent partial charges, a partial negative on the oxygen and partial positives on the hydrogens. In the case of van der Waals interactions, you don't have permanent charges because when we're looking at a molecule like hydrocarbon, here's a hydrocarbon here, and this is 1, 2, 3, 4, 5, 6, 7, 8. So this is octane? Yeah, octane. Remembering my organic chemistry. So octane itself has no charge on it. No partial, no full, nothing. It's just carbon and hydrogens. Now octane is a liquid at room temperature with a boiling point of 125 degrees. It has a higher boiling point than water. So what is keeping octane molecules near each other? I mean, something has to be keeping them near each other for them just not to fly off and be a gas. So what happens is when one octane molecule gets near another octane molecule, what's surrounding each molecule is their electron cloud. So I'm just going to kind of dash around the electron cloud right here of this guy, and this other octane molecule, I'll put it in red. And here's the electron cloud of this guy. So, and electrons are negatively charged. And same charges, negative and positive, will repel each other. So when these electron clouds get near each other, what will happen is they'll sort of start to repel each other at certain points. So what you can imagine is that once they get near each other, is that at some points along this chain, the electron cloud of one will push against the other and make those electrons sort of spend more time on one side. So let's imagine that in the case of this guy right here, that at this point, the electrons have been sort of pushed, but now they're more over here, right? And at this point, the electrons are pushing out, and so in the backside, there's a little bit less, and etc. Let's say here they're getting pushed back a little bit. I'm sort of really exaggerating here to try to make the point. So if you have this pushing effect, what will happen is you have more electrons spending more time here, so you have a partial negative charge and a partial positive charge here. In this case over here, you'll have a slight partial negative and a partial positive here. And again, here you'll have a partial positive because the electrons have been pushed to the back. And now what will happen is the electrons on this one will spend more time here, but less time here, right? And here they're getting pushed back, so you'll have the opposite. And here they're in this direction, but a little bit less here. So what you'll have is a partial negative here, a partial positive here, partial negative here, and on the back end you'll have the opposite. So this was partial negative, partial positive, right? So you can imagine if you have another octane molecule here, you'll have the same thing happen where you have these sort of partial negative and partial positive. Now these are not permanent, meaning that this picture that we have here right now, this will change the next fraction of a second, where these partial negative and partial positive charges are sort of appearing, disappearing, or changing signs. But as long as the surface contact between the two molecules is large enough, you're going to get many of these. And the more you have, the stronger their interaction is between the two different molecules. That's why if you kind of look up the boiling points of hydrocarbons, You want linear hydrocarbons, ones that don't have branching points. If you sort of look them up and go from methane to ethane to propane, etc., and you keep going up and you increase the chain by 1 carbon, you can see that the boiling point keeps increasing, meaning now that there's more surface area interaction between those two molecules, so you have more of these van der Waals interactions where the electron clouds push against each other and create these spontaneous partial negative and partial positive charges opposite each other, and that leads to them sort of sticking together pretty strongly where you get very high boiling points. Now, the only thing that is required for this to happen is that these chains have to be sort of pushed near each other. And that is accomplished through another phenomenon. So each van der Waals interaction is much weaker than a single hydrogen bond. The greater the surface area of contact between the nonpolar surfaces, the greater the number of van der Waals attractions. The additive effect of all the van der Waals attractions can lead to a strong interaction between the two surfaces. Now, the word strong interaction, maybe I shouldn't have used this here. I do not want you to mistake that this will turn into a covalent bond. It is not a covalent bond. The strength of the interaction increases the more surface area you have. For example, hexane. A hexane molecule will have more surface area with another hexane molecule than it would with, let's say, a propane. Right? So as long as the surface area between the two molecules is large enough, the hydrocarbons, you're going to get more of this push back and forth between the electron clouds, creating those partial positive and partial negative charges, leading to these van der Waals interactions. So the strength of strong and weak interactions here. So you can see that we have the strengths in vacuum and in water. And we really don't care about vacuum because we're studying biology, so we really care about what's happening in water, right? So, but the vacuum data is actually kind of neat, and it gets to something else. A single covalent bond is very strong, and it's the same in vacuum and in water. Nothing, it doesn't affect it. Now, in parentheses, that's in calories, and not in parentheses is in kilojoules per mole. So you can see that in vacuum it's 377, and water is 377. Ionic is very strong in vacuum, 335. But in water, it goes to 12.6. So a single ionic bond is not that strong compared to a covalent bond when it's in solution in water, right here. Hydrogen bond, it's about a third in strength in water than it is compared to the ionic bond, so it's weaker. Again, you have partial charges involved here, so it'll be a weaker interaction. And van der Waals interactions are the weakest, but we're talking about a single van der Waals interactions. That's why if you have a long hydrocarbon chain, more surface area, more non-polar surface area, you get more of these. And as you get more of these, it's an additive effect. So if you have 10 of them, you'll have a interaction of 4 kilojoules per mole. You have 100, it's 40 kilojoules per mole, and etc. and etc. So a single weak interaction by itself is not that strong, but if you have multiples, they can become as strong as a covalent bond because it's an additive effect. So, for example, if I have 4 hydrogen bonds, I have an interaction of nearly 50 kilojoules per mole for that bonding interaction if I have 4 hydrogen bonds forming between 2 molecules. So why is it that ionic bonds are much weaker in an aqueous solution, in a solution where the solvent is water? Well, that's because water molecules start to get in the way of ionic bonds forming. So you can see here, the magnesium 2+ right here is surrounded by water molecules, and it cannot get near this phosphate with its 2 negative charges, so it can't form an ionic bond. So the water molecules kind of get in the way and disrupt ionic bonds from forming, and that's why ionic bonds are much weaker in an aqueous solution than they are in a vacuum where there's no water. So enter an intramolecular weak interaction. So intermolecular weak interactions is when you have 2 molecules, for example, water and let's say a carboxylic acid group, which has a negative charge. We can just call this an amino acid. Let's say this is an amino acid here. And this is a a hydrogen bond, a weak interaction between two different molecules, right? Now, when we're talking about an intramolecular weak interactions, imagine that you have, for a molecule, let's say this is our molecule right here. It's a long molecule. You have an OH group here, and you also have a carboxylic acid group here. And you have a hydrogen bond forming here. Now, this hydrogen bond is forming in the same molecule, meaning that this is a single molecule and you have an intramolecular weak interaction happening within the same molecule. So that would be an intramolecular weak interaction. Now, the additive effect of many weak interactions will lead to a strong interaction. This picture right here is showing you two binding surfaces between two different molecules. Imagine these are two proteins. So you have one protein, let's say call this A, we'll call this B, and A and B will bind to each other, forming a complex, but they do so because when these binding surfaces that we have here and here get near each other, they geometrically fit for one thing, but when they do fit, you have these weak interactions occurring right across from each other. Basically have some sort of positive and negative charge right around each other. And it doesn't have to be a full charge. What these positive and negatives are showing you is that there's either a partial positive, partial negative, or a full positive and a partial negative, or etc., right? It's just that you have opposing permanent charges on either side, and when they get near each other, they lock in. Now, individually, these weak interactions are weak. They're weaker than a covalent bond, and in an aqueous solution at 37 degrees Celsius, they can easily be disrupted if you just have a single weak interaction happening. But if you have multiples, there's an additive effect where you add up those kilojoules per mole, and that can lead to it being very strong, where these two molecules actually stay together much longer than if they only had a fewer number of weak interactions. So they bind to each other and they stay together a longer period of time before the random thermal motion that's caused by the temperature of the solution makes them come apart. And that's something that we'll get into later and talk about a little bit more later, but it's something to start thinking about. That when you have A plus B giving you the complex AB, that this single arrow being shown here is actually not a single arrow, right? So what it actually is a double arrow. When two molecules form a complex, that complex will get disrupted, meaning that the two molecules will come apart, but they'll reform and form a complex again. Weak interaction is reversible, whereas a strong interaction, covalent bond, can only be broken through chemical reactions. So there's a term, reversible binding. And what we mean by binding, we always assume that we're talking about reversible binding. What is reversible binding? If I have, for example, two water molecules that are hydrogen bonding with each other, if I put in a little bit of energy, increase the temperature of the solution, etc., and they come apart, where they're no longer forming that weak interaction, that hydrogen bond, I started with two water molecules, two H2Os, and I still have two H2Os on this side. Nothing has changed. So when you have weak interactions, if you disrupt them, the identity of the molecules that you started with are the same as the identity of the molecules when you break those weak interactions. You don't change that. Whereas when you break a strong interaction, for example, a dipeptide, if I break these into two amino acids with a hydrolysis reaction plus H2O, what do I end up with? I end up with two amino acids. So what do I have on this side? I have a single dipeptide and one H2O molecule. And on this side, I have two glycine. So you can see the identity of the molecules on the left side are different than the identity of molecules on the right side. So in scenario 1, the identity on both sides are the same, whereas scenario 2, the identity on both sides is not the same because I've broken a strong interaction, a covalent bond in scenario 2. So that's the difference between reversible binding and non-reversible binding. Non-reversible just means that in order to break that binding interaction between two molecules, that binding interaction has created a new molecule. And to break that, you actually needed a second chemical reaction to either break it or reform it. And we'll stop here and continue in the next video.